So what I want to do in this video is show that you can look at observer O and observer O prime together in one space-time diagram, together on a space-time diagram. So this is in contrast to normally thinking, so I've got X and T that belong to O, right? And separately having X prime, T prime that belong to O prime, and having essentially this list of Lorentz event transformations, right? And so in this coordinate system, there's an event, and in this coordinate system, it happens in general at a different pair of coordinates. This event's got T prime X prime coordinate location, and this event's got T X, right? And this observation frame moves towards the right at speed u, right? You know this story, in observer frame O. And in general, they're going to have different values for the space-time coordinates for events. Okay, so the way I'm going to do this is to remind you, so remember O and O prime, we're going to use this specific relationship, have a specific relationship, that is, their directions are common. For example, X, so the positive X and the positive X prime directions are the same, right? And Y prime, Z and Z prime, etc. Those are all the same. Yeah. So that's one of the relationships. The other is the coincident origins. So the coincident origins, coincident origins at x equals to 0, t equals to 0. So the idea is that this coincides with x prime equals to 0 and t prime equal to 0. Yeah, so it just means that these people, or these two different right, observation frames, they set their clocks to 0, and they understand the origins of their coordinate systems to be marked 0 at the moment that, say, O prime is right on top of O. So everybody sets to 0 here, and then stuff, is relativistic afterwards. Or, I mean, it's actually relativistic during as well. But anyway, so there's a coincident origin, and these things right here are why we can write this stuff down, right? So the directions are common. Here's two common directions here. There's relative motion. Oops, this is the other thing. Relative motion in x direction. That was the thing that I forgot to write down. So actually, I should include this in our specific relationships. So the relative motion is in the x and x prime direction. And you could say that O prime moves in positive x direction in O at speed u. Okay, so yeah, I think that this is enough to say what the specific relationship is between O and O prime. And once we agree that this is a good starting point on the relationship, then we can draw a meaningful drawing that has both O and O prime together in a spacetime diagram. Okay, so let me remind you of something kind of strange. So look at O by itself. Right? So let's talk about something. So this is the x direction, and this is the time direction, and we're talking about O. And if I think about it, the t axis is the world line, right, of the x equals to 0 location in O, right? As an aside, a stationary object has a vertical world line. So here is x, t, and we'll say that the object is stationary in O. So here is its location. That's the position of the object. And for all future time, that's its location. It's not going to wander right on the x-axis. And for all the previous time, right? So this is an object that's standing still. Its world line is a vertical line. So if we look at O by itself, in O, there is a position on the x-axis called x equals to 0, and in O, that position stands still. So that location, that position, has a world line that just extends into the future as a vertical line upwards and came from the past from below with a vertical line, right? So the t-axis is the world line of the x equals to 0 location in O. So what is the x-axis? The x-axis is the set of all space-time points such that t equals to 0, right? So here is t equals to 0. It is all of the points that satisfy t equals to 0. So that is what the x-axis is. So what we're doing is identifying, these are the meaning of the axes, right? So the question is going to be, what do these axes mean inside of O? That's how we're going to do this. So let's answer the question. In O, what are the t prime and x prime axes, right? So let's draw O. And I'm going to be careful to draw O with a little bit of negative x and a little bit of negative t. So this is O. And so here is t and x. All right. And so remember that the t-axis is the world line of the x equals to 0 location in O. So I'm going to translate this statement here and say that the t prime axis is the world line of the x prime equals to 0 location, right? And remember that O prime moves in the positive x direction inside of O at speed u. So that means that the x prime equals to 0 location moves like this too, right? So what I'm going to do is go into O and draw the x prime equals to 0 location world line. There it is. It's drifting up along the x-axis as time goes into the future, and it does so with a slope. The slope actually is c over, no, I'm sorry, it's not c over u, it's 1 over u. That's the slope of the t prime axis inside of O, right? The slope is 1 over u. So let me show you why the slope is 1 over u, where u is the relative speed between O prime and O. So, so what we do is we look at the Lorentz transforms. See, the Lorentz transforms tell us the relationship between event coordinates in O and event coordinates in O prime. The t prime axis is the world line of the x prime equals to 0 location. So x prime equals to 0 equals, right? Here's x prime. So it's gamma of u times x minus ut. And so what this does is x prime equals to 0. So that means 0 equals this stuff here. Remember that gamma of u is never 0. It's bigger than or equal to 1. So I can divide by it and, divide it away. So there's no danger of it being 0. And what you get is that you get the relationship that x equals to ut, but I'm going to turn it on its head and write t equals to 1 over ux. And so what this looks like is y equals to mx plus b, right? Equation of a straight line. There is no addition over here, right? And the reason that's 0 is actually because of this coincident origin relationship. And so right here, this is a straight line. And this straight line is the t prime axis. And the t prime axis actually is in both directions, just like the t axis is, right? And can you see that here is the slope, 1 over u. So this is the equation of a straight line, and that straight line is the set of xt spacetime locations that mark the world line of x prime equals to 0, which is called the t prime axis. So there's the t prime axis inside of O. The x prime axis is the set of all events, event points, such that t prime equals to 0. So t prime equals to 0, here is the relationship, here's t prime. So that means that 0, which is what we're setting t prime equal to 0, it's equal to gamma of u, and then we get t minus u over c squared x, and this implies that t equals u over c squared x. So this right here is an equation of a line that is the x prime axis, right? So you'll notice that u over c squared is the slope, and this slope is bigger than 0, so it's a positive slope. But the u over c squared slope, if you think about it, is smaller than this slope. And it's because c is bigger than u. You can't have observer frames move faster than the speed of light. So the slope of the x prime axis is actually smaller than the slope of the t prime axis. So the t prime axis is steeper, and the x prime axis, right, has a slope of u over c squared. And I can, and that line is a straight line. So this is how O and O prime are together on the same spacetime diagram, right? So I'm going to do a little bit of an abstraction, but this is the idea. Actually, what I should show you is how t and t prime. Let me show you something really quick. So this is the x-axis and the t-axis. And actually, yeah, so I'm going to exaggerate it a little bit. So here is the t prime axis. And here is the x prime axis. All right? And here is an event. So the way that, so O measures event E, and in a sense, how O does this is O assigns the x position to be here and the t position to be here, right? So this dashed line is parallel to t, and this dashed line is parallel to x. I hope you can see that, right? So the way that the event coordinate is located on against the axes as you go back parallel to the x-axis to the t-axis, and you look on the t-axis ruler for its value, and you likewise you do kind of the same thing on the x. But the weird thing is, how do you do this on x prime t prime? Well, you have to do the same thing. So in order to figure out the x prime value, you have to go parallel, right, to the t prime axis. So that location right here is x prime. And the way you get the event coordinate along the t prime axis is you go back to the t prime axis parallel to x prime. Right? So that's meant to be parallel to x prime. And this is t prime. And you can kind of see that this geometry includes Lorentz transforms. Right? Can you see that x and x prime, right, kind of read differently? Another thing is you can actually see the relativity of simultaneity. So let's say this is event A, right? And so it's given x sub A and t sub A as space-time coordinates according to O. And here is an event B, right? Which is, it happens at the same time as A according to O. But if you look according to O prime, can you see that event B happens at a later time than event A? So according to O, T sub B minus T sub A equals to 0. This is what simultaneous means. According to O prime, T sub B prime is actually bigger than T sub A prime. So event A happens first, right? So this is the relativity of simultaneity. So the notion of simultaneousness is relative to the relative motion of observers. I think this is extremely cool. I hope you agree. Okay, so what I'm going to do is let's be a little abstract about dimensions. And it's not really an abstraction, but what I'm going to do is the following. So this is what's going to follow. We're going to have a bit of a dimension abstraction. All right. So what that looks like is this. So we have, I hope that if you've been following what I'm about to draw makes some sense, or at least you know it comes from somewhere, and you can go back and read and rewatch this video and try to see where stuff comes from. What I'm going to do is, instead of t and x, I'm going to study c times t and x. And the reason that I want to do that is, what it does is it makes the axes have common units. They're at least common dimensions, because, you know, speed times time is a distance, so these are distances now, and these are distances as well. And it's convenient to think in terms of that unit called the light year. So I can talk about numbers of light years over here, and now that this is a distance, I can also do light years here as well. So I'm going to compare CT to c times t prime. Conveniently, c is the same for all observers. So the value of c is just the same. It doesn't matter who is the observer, right? So c times t and c times t prime. And over here, I'm going to study x prime. Okay, so with my Lorentz transformations, I can just go ahead and do it here, actually. So x prime is equal to gamma of u, right? And then x minus u times ct over c. I wonder if you can see that all I did was multiply and divide by the same factor, but what that makes me able to do is have this combo quantity called ct. And likewise, I can do it in t prime as well. So t prime, I'm going to multiply by c, is equal to gamma of u, right? So there's ct prime. And then I'm going to multiply by c throughout the right-hand side as well. So it's ct, so now I have ct and ct prime. And then multiplying by a factor of c on the second term just gets rid of one of the c's on the bottom. So it goes minus u over c times x, right? And so if I go And okay, so I've got that. So this world line right here, this line is actually, if you remember, it comes from this business here. I'm gonna do it kind of quick. What this says is the CT coordinate value is equal to, right, C divided by U times X, right? And so on a graph where the vertical axis is CT, that's the dependent value, these are the set of spacetime event points such that CT equals to C over UX, which means this has a slope of C over U, right? So the slope of the CT prime axis is C over U. What's interesting is when you go and you look at the set of all T prime equal to 0 events, right? This you set that equal to 0, and then you go in here and you look at solving for CT. This says that CT equals to, and it's got the U over C times X. So that means that the slope here is actually just the inverse. Okay, so what that does is because units are common on both axes, what I mean by that is the CT units are light years and the X units are also light years, right? We can do trigonometry. Right? So what you can do here is you can say that there is an angle. I'm going to call it an angle phi. And if you think about it, the sine of the angle phi is equal to, right? It's going to be, for example, if you just pick any sort of x value and make a triangle, right? Whoops, I don't mean the sine of phi. Sorry. I mean the tangent of phi. So the tangent of phi is the opposite over the adjacent. And the opposite over the adjacent is actually the rise over the run. And the rise over the run is the same as the slope. Like this. And this angle phi, if you think about it, over here, if you draw a triangle, right, you just pick a CT point, then at CT, if you imagine this angle here, it turns out that this is also phi, because you know, when we imagine looking at the axes this way, the rise and the run, they kind of get flipped. And so this actually is also phi. So if I go and I scale the time axes with an extra factor of c, what it does is it lets me talk about an angle, and this becomes really a geometry problem. That is, Lorentz transforms are just the geometry of spacetime. Yeah, and it's, but you kind of have to like do a little bit of an abstraction. We're talking about somewhat of a new sort of like, you know, time coordinate that is treated more like a space coordinate again. Yeah, cool. So this is all I wanted to say about this.